It began with silence. The kind of deep, infinite silence that only space can hold. A quiet so profound that even light itself seems to hesitate as it crosses the void. But just 3 minutes ago, that silence trembled. Something shifted in the dark tapestry of the cosmos. A faint, uncertain gleam appeared in the night sky, one so subtle that only the patient eyes of an astronomer could notice it. That glimmer would soon become the center of global attention, the spark of a mystery still unfolding. Tonight, we begin a story not of what is known, but of what has just been seen, and of what it might mean. A new object has entered the narrative of our solar system. It is called S2025 Borisov, a name that already carries weight in the world of astronomy. Drifting silently between Earth and the enigmatic interstellar visitor known as 3I Atlas, this faint but growing point of light defies what scientists expect from a comet. Bright, yet almost tailless. Dynamic, yet strangely calm. What we are witnessing may be the beginning of an alignment, a collision, or something that no one yet fully understands. For now, it remains a question suspended in the cold air of the November sky. To understand why this is extraordinary, we need to return to a single observatory, a single night, and a single human being. One who looked a little longer than others and noticed what no one else did. In the early hours between the 2nd and 3rd of November, at the Virgo Observatory in Crimea, astronomer Gennady Borisov examined a new series of exposures. Against the stillness of the star field, a faint spot moved, subtly but unmistakably. It was not an asteroid from the main belt. Its trajectory did not align with any known minor planet. It was something else. In those quiet moments of observation, time itself seems to slow. Each image tells a story measured in minutes and arc seconds. Borisov compared frames, verified coordinates, adjusted focus. The spot held, its motion precise, deliberate. He prepared a report to the Central Bureau for Astronomical Telegrams, a message that would ripple across the global astronomical network before dawn. The brightness was measured at 12.1 in stellar magnitude. A diffuse coma, about half an arc-minute in size, surrounded the nucleus. But there was no visible tail. The signal was sent. Something new had entered the field of vision. Names in science carry echoes of their past, and Borisov's name resonates deeply. In 2019, using a telescope he built with his own hands, he discovered the first confirmed interstellar comet ever observed, 2I Borisov, rewriting what we believed about visitors from beyond our solar system. Now, 6 years later, the same patient eyes and handmade optics had found another anomaly, one that refused to fit comfortably into the models astronomers rely on. Was it coincidence, or was something guiding these discoveries, pointing toward a larger cosmic pattern, yet unseen? As news spread, observatories from across the world, Russia, Japan, Ukraine, and the Canary Islands, rushed to confirm. Images began pouring in, datasets multiplying. Each team saw the same strange form, a condensed coma without the long, vaporous trail that defines a comet's classic shape. 2 out of 10 early reports hinted at a faint, intermittent tail, but most saw none at all. In this absence lay the seed of curiosity, the kind of question that fuels entire careers. What kind of comet refuses to grow a tail when bathed in sunlight? By November 3rd, confirmation came. The object was catalogued globally as S2025 V1 Borisov, and a new wave of urgency swept through the scientific community. Amateur astronomers and professionals alike turned their instruments toward it, measuring brightness, plotting orbital paths, searching for spectroscopic clues that could explain what they were seeing. Each observation added a brushstroke to the growing portrait of an object both familiar and alien. From Palomar to Sukagawa, from Lviv to La Palma, each telescope recorded the same enigma. Brightness increasing, structure consistent, tail absent. What began as a faint, forgotten glimmer now demanded attention from the entire world. Something was happening between Earth, 3I Atlas, and this new traveler. Something that defied not only prediction, but intuition. Was this an illusion of geometry? A momentary cosmic coincidence? Or the start of a celestial choreography written long before we existed to watch it unfold? And as we turn our gaze upward, one question remains suspended in the vast silence. What have we really discovered? The confirmation of S2025 Borisov ignited one of the most rapid scientific responses in recent astronomical memory. Within hours of its official designation, data streams from dozens of observatories began to converge. The first task was simple, yet profound: to determine where this object came from and what it was made of. But the results, as they came in, only deepened the mystery. The newly found body shone with an unusual steadiness, its magnitude brightening almost exponentially. Yet its structure remained stubbornly unchanged. There was no sign of the shimmering, elongated tail expected from a comet nearing solar radiation. What scientists saw instead was a compact, rounded glow, a coma dense enough to obscure its own nucleus, as though the object guarded its secrets behind a curtain of dust. The discovery unfolded in a rhythm of rising astonishment. Observatories in Japan, Crimea, and La Palma compared simultaneous exposures and found that S2025 Borisov was brightening faster than any predictive curve could explain. Normally, as a comet approaches the Sun, sublimating ices create jets that drive visible changes in brightness and form. Yet this one displayed a different pattern. It brightened evenly, almost mechanically, suggesting an alternative energy process or an atypical composition of volatile material. Some speculated that its surface might be coated with carbon-rich compounds that sublimate at slower rates, producing light through reflection rather than active release. Others proposed that the nucleus was unusually large and dense, holding its structure under conditions that would usually fragment smaller comets. At the European Southern Observatory, computational dynamicist Dr. Larissa Meinhardt began reconstructing its orbital path. Using astrometric measurements gathered from across 3 continents, her team plotted the object's position relative to the known orbits of 3I Atlas and S2025 Atlas. The solution startled them. The new comet was moving on a steeply inclined orbit that placed it between the Earth and 3I Atlas from our line of sight. Its perihelion, the closest point to the Sun, was projected for mid-January of 2026, placing it in an area of gravitational tension between the inner planets. But what fascinated Meinhardt's team most was the similarity in trajectory to that of the interstellar visitor 3I Atlas. Though the two were separated by tens of millions of kilometers, their apparent alignment in the constellation Virgo created the illusion of proximity. This was no collision course. It was a rare moment of visual resonance, a perfect overlay of cosmic timing. By the morning of November 5th, professional and amateur networks had gathered enough photometric data to model the brightness evolution. The increase of 5 stellar magnitudes in 5 days suggested that the comet's surface reflected almost 100 times more light than at discovery. That rate of change did not match any known volatile composition. Classical comets, rich in frozen water, carbon dioxide, and ammonia, tend to exhibit nonlinear brightening correlated with distance from the Sun. The Borisov object, however, brightened without corresponding thermal thresholds. Its light curve resembled not the pulse of an evaporating body, but the reflection of a surface that was already illuminated. It was as though the comet were covered in glassy minerals or metallic dust, capable of scattering sunlight with abnormal efficiency. Theories began to diverge. Some astronomers proposed that the new object might be a fragment of an earlier interstellar body, possibly debris ejected from 3I Atlas itself during a previous outgassing event. Others countered that its orbital velocity was too low for interstellar origin and too high for a simple solar system asteroid. In the middle ground stood those who believed S2025 Borisov represented a transitional type of body, an ancient comet nucleus that had lost most of its volatiles and now reflected sunlight from a crust of refractory materials. Whatever the case, its presence between Earth and the interstellar visitor was enough to stir whispers of cosmic coincidence. Meanwhile, the global observation campaign reached an unprecedented scale. The Palomar Observatory reprocessed archived sky survey data and identified faint traces of the Borisov object from late October. That meant the comet had already been within observable range days before its official discovery. In those earliest frames, its brightness was approximately 17.5 magnitude, barely detectable, but its subsequent surge could only be described as explosive. Within less than a week, it became bright enough for small amateur telescopes. The transition fascinated astrophysicists. Some likened it to the spontaneous ignition of a celestial ember, others to a delayed reflection of sunlight off slow-moving dust particles. Spectroscopic attempts were quickly organized. The Nordic Optical Telescope captured a low-resolution spectrum showing a near-featureless continuum with faint traces of carbon and cyanogen, typical signatures of comets, but at levels much weaker than expected. A team at the Mauna Kea Observatory attempted to detect water vapor lines through near-infrared emission, but reported nothing definitive. Without strong volatile emission, the classification of the Borisov object as a comet remained technically uncertain, yet its diffuse coma and steady motion clearly excluded it from the category of asteroids. It occupied a liminal space between definitions, a visitor that refused labels. At the same time, orbital mechanics experts from the Jet Propulsion Laboratory recalculated its motion using data from over 100 observatories. The path traced a delicate curve rising from below the ecliptic plane, crossing near Earth's orbital distance at about 0.55 astronomical units. If projected backward, the orbit intersected regions of the outer solar system seldom visited by long-period comets, suggesting a possible origin in the distant Oort cloud. Yet the geometry hinted at something stranger, a faint gravitational perturbation consistent with passage near another massive body, possibly Jupiter, within the past decade. That deflection might have bent its orbit into this unusual configuration, placing it momentarily between our planet and the outgoing interstellar atlas. In the astrophysical community, the coincidence of timing could not be ignored. Only twice before had astronomers witnessed two bright comets simultaneously visible in the same region of sky, and never had one been interstellar. This event, therefore, offered a once-in-a-century opportunity to compare the behavior of a solar system-born object with that of a visitor from beyond. The difference between them was profound. Atlas followed a hyperbolic trajectory, its speed carrying it away forever from the gravitational grasp of the Sun. Borisov, however, was bound, an object of our own system, moving through a stable, though eccentric orbit. And yet, they looked eerily similar, both bright, both nearly tailless, both defying expectation. As data accumulated, teams began to focus on the peculiar physics of the coma. Under standard models, solar radiation pressure acts on dust grains expelled from a comet's nucleus, pushing them outward to form the tail. The ratio of that pressure to the Sun's gravity is defined by the dimensionless parameter V, beta. For typical fine dust particles, V exceeds 1, meaning sunlight effectively blows the particles away. But if the particles are large, millimeters or even centimeters across, V falls below 1, and solar radiation is too weak to displace them. Instead of streaming outward, the dust lingers close to the nucleus, thickening the coma while leaving no visible tail. When researchers modeled the Borisov data under these parameters, the results fit surprisingly well. The comet appeared to be shedding massive, heavy grains, possibly fragments of crust fractured by internal stresses rather than by thermal sublimation. In Japan, the Asuka Observatory captured long exposure frames revealing subtle asymmetries within the coma, faint arcs that hinted at rotation. The nucleus seemed to spin slowly, perhaps once every 10 to 12 hours, throwing off dust in rhythmic bursts. If true, that could explain the periodic variations in brightness observed across different nights. The rotation period was later refined through photometric modulation studies, which found a small but consistent brightness oscillation of about 0.2 magnitude. This subtle flicker became the heartbeat of the comet, marking time in a language written in reflected sunlight. By mid-November, an extraordinary scene unfolded in the skies before dawn. 3 comets, 3I Atlas S2025 5V, 1 Borisov, and S2025 K1 Atlas, occupied the same general sector of the celestial sphere. To the naked eye, under dark skies, they appeared as faint smudges, 2 bright and 1 golden. For photographers, it was a rare tableau. Astrophotographers from both hemispheres captured wide field images showing the trio suspended against the stars of Virgo and Leo, each glowing with its own distinct tone. Atlas, the interstellar traveler, shone in pale white. Borisov, the newcomer, in soft bluish gray. And the distant K1 Atlas, in a golden hue. None showed the expected tails. The spectacle confounded, inspired, and united thousands of observers in a shared wonder. And still, the mystery deepened. Solar activity surged in those days. Intense flares erupted from the sun's surface, sending waves of charged particles across the inner system. Comets in such moments usually respond dramatically. Their tails expand, their brightness spikes. But these 3 remained curiously stable. The absence of reaction to the solar storms suggested a surface composition highly resistant to heat and radiation. Perhaps, some proposed, these were relics of a primordial epoch, containing materials forged before the solar system fully formed. Others wondered if they were fragments from a disintegrated body that once roamed the interstellar medium, captured separately by the sun's gravity. The China National Space Administration's Tianwen orbiter circling Mars was instructed to point its low-resolution imager toward the Borisov region in early November. The resulting footage was brief and grainy, yet unmistakable. A condensed sphere of light, no visible tail, steady luminosity. The recording confirmed what ground-based astronomers had seen, but provided little else. Nonetheless, the data held significance. It represented the first time a Martian orbiter had recorded a newly discovered comet simultaneously observed from Earth. It was a reminder that humanity's eyes now look out from multiple worlds. Meanwhile, at NASA's Goddard Space Flight Center, teams proposed to allocate time on the James Webb Space Telescope for a short sequence of near-infrared exposures. The goal was to detect the spectral fingerprints of carbon monoxide, water, and silicates within the coma. If approved, those observations could distinguish between an icy nucleus and a rocky or metallic one. But competition for Webb's observation slots was fierce, and the review process deliberate. As days passed without confirmation, scientists grew restless. Each dawn brought new amateur images, but without high-resolution space-based data, the true nature of Borisov's nucleus remained veiled. Still, the ground network persisted. From Poland to South Africa, from Chile to Australia, observers logged coordinates, brightness estimates, and morphological notes. The international collaboration resembled a vast symphony of measurement, each telescope a voice contributing to the evolving harmony of discovery. The collective results painted a portrait of stability amid change. The Borisov comet held its brightness near magnitude 10.9, even as it approached the Sun. Such steadiness, rare among comets, hinted at a solid cohesive structure rather than a fragile ice conglomerate. Speculative debates bloomed in academic circles. Could Borisov represent a new category, a cometary asteroid hybrid, sometimes called a Manx comet, lacking volatile material but retaining a faint coma of dust? The absence of gas signatures supported this idea, yet the object's visual intensity exceeded that of typical Manx candidates. Others suggested it might be an interstellar shard decelerated by gravitational interactions within the solar system, captured into a bound orbit. The probability of such capture was astronomically small, but not zero. After all, the discovery of 2I Borisov in 2019 had already taught the scientific world never to dismiss the improbable. In late November, the discussion turned toward the possibility of non-gravitational acceleration, the subtle recoil forces caused by uneven outgassing. When analyzed, the orbital elements of Borisov showed negligible deviation from purely gravitational motion. That stability contrasted sharply with the behavior of interstellar objects like Oumuamua, whose unexplained acceleration had stirred years of debate. In Borisov's case, the lack of such forces pointed to an inert, possibly rocky nucleus. It moved like a stone through light, silent, steady, indifferent to the heat that tried to stir it. The combination of these findings formed a paradox: a bright comet without a tail, a reflective surface without volatility, a stable orbit in a region dominated by dynamic activity. Astronomers were left with the same unease one feels when encountering a familiar pattern in an unfamiliar context. Was this an anomaly of physics, or a sign that our definitions had grown too narrow? In the pre-dawn hours of November 7th, as telescopes across both hemispheres captured simultaneous images of Borisov and Atlas, a new awareness began to form. This was not just an observational event. It was an experiment of nature itself, a window into the diversity of matter drifting through space. The laws of celestial mechanics still held, yet the manifestations of those laws were richer, stranger, and more nuanced than the textbooks suggested. The night sky had once again proven its capacity to humble us, to show that even after centuries of mapping and measuring, we remain explorers, standing on the threshold of the unknown. And as the days lengthened and new data continued to arrive, one truth became clear. Whatever S2025 V1 Borisov truly is, it has already altered the course of how humanity watches the heavens. Each photon reflected from its surface carries not only the signature of a distant object, but the reminder that discovery is not a single act. It is a continuous unfolding, an echo that expands through both space and time, inviting us to listen closer to the silence that came before it. To understand the magnitude of this discovery, one must first understand the man behind the name. Gennady Borisov is not a product of large institutional machinery, but of quiet persistence and curiosity, a solitary astronomer working beneath the wide, cold skies of Crimea. In an era where automated surveys sweep the heavens with robotic precision, Borisov remains a craftsman of observation. He built his telescopes by hand, not from wealth, but from will, assembling mirrors and mounts in a modest workshop. His first major triumph, the detection of 2I Borisov in 2019, came not from a national agency or a massive observatory, but from the careful patience of a single human being staring into the night. That discovery, the first confirmed interstellar comet, became one of the defining astronomical events of the 21st century. It was proof that the void between stars was not empty, but alive with drifting relics from other suns. Now 6 years later, history has echoed itself. In the same landscape, through the same home-built optics, Borisov once again captured something that eluded the rest of the world. S2025 V1. Borisov is not simply a comet. It is a reflection of how scientific discovery often begins, not in the grand halls of research institutions, but in the stillness of an individual night, guided by intuition rather than command. His work reminds the world that wonder remains democratic, that the sky belongs to whoever dares to look long enough. The telescope that made this possible affectionately called Gen 6 among amateur circles, is a masterpiece of improvisation. Its mirror, polished by hand, measures 65 centimeters in diameter, mounted on a motorized equatorial platform that Borisov himself engineered to track objects with extraordinary precision. The optics were designed not for beauty, but for efficiency. Each screw, lens, and wire placed with a purpose. Through this handmade eye, faint whispers of light cross distances measured in hundreds of millions of kilometers, transforming into discovery. It is through this same telescope that he once again broke through the threshold of the unknown. But while one man may begin such a journey, it is the collective body of science that carries it forward. Following the initial announcement, dozens of teams joined the pursuit. Some worked through the night to refine the orbit. Others analyzed spectra, while a growing group of data modelers attempted to simulate the strange brightness curve. Together they formed a network spanning continents, a living embodiment of modern astronomy's collaborative spirit. What began as a small local observation grew into an international campaign uniting experts and enthusiasts across the globe. And yet, for all the progress, S2025V1 Borisov continues to defy clarity. Every telescope that turns toward it seems to find more questions than answers. High-resolution instruments reveal that its coma is layered, showing subtle gradients in brightness that suggest shells of dust expelled in uneven intervals. Polarimetric studies show that its grains scatter light in ways unlike typical cometary dust, as if the surface contains metallic or carbonized fragments, materials that could trace back to the early solar nebula. These details open an avenue into the deeper narrative. This object may not merely be a curiosity, but a key to understanding how matter behaves under extremes of isolation, radiation, and time. Some scientists now suggest that Borisov's new discovery represents an ancient survivor, a body forged in the earliest days of the solar system when the planets were still forming and collisions were frequent. Over billions of years, most such fragments have been drawn inward, melted or ejected into interstellar space, but a few may have drifted silently on the outskirts, dark and dormant, until a subtle gravitational resonance brought them back toward the light. If S2025V1 Borisov is one of these survivors, its composition could offer a direct glimpse into the unaltered materials that predate Earth itself. In that sense, every image taken of this object is more than documentation. It is time travel, a record of something that existed before our species, before our planet, perhaps before the very balance of the solar system as we know it. The light reflected from its surface left only minutes ago, but the atoms within it carry the memory of eons. To study it is to read a sentence written at the dawn of creation. Meanwhile, the role of the Atlas comets cannot be ignored. 3I Atlas, the interstellar visitor, continues its outward journey, fading as it drifts beyond the reach of ordinary observation. S2025K1 Atlas, with its golden glow and steep inclination, follows another path entirely, reminding us that the heavens are not static but dynamic, filled with independent travelers intersecting by chance and perspective. The temporary alignment of these three comets in early November, Borisov, 3I Atlas, and K1 Atlas, is more than a coincidence of geometry. For astronomers, it is a living diagram of cosmic diversity. 3 separate origins, 3 different compositions, 3 expressions of matter under the same starlight. There is poetry in the idea that across countless years of cosmic emptiness, these bodies now share our sky at once. From one vantage point on Earth, they appear close, a fragile illusion of proximity. Yet in truth, they are separated by tens of millions of kilometers, each following its own lonely path. That paradox, closeness in distance, unity in separation, mirrors our own search for meaning in the universe. Humanity, too, looks out across unimaginable gulfs, seeking connection, seeking reflection. In the glow of these comets, we see not only physics but philosophy. The international community continues to refine its instruments in pursuit of sharper answers. There is talk of deploying adaptive optics from the Very Large Telescope, of requesting a brief observation window on the Hubble successor, telescopes in low Earth orbit, and of recalibrating ground-based radar arrays to detect the faint backscatter from the dense coma. Every attempt brings a fraction of progress, but the larger mystery persists. The data show that S2025 V1 Borisov rotates slowly, its surface locked in a dance between sunlight and shadow. That rotation might explain its unusual luminosity, as wide, flat surfaces alternately reflect and conceal light. If true, then what appears to be a constant glow could in fact be a carefully timed rhythm, a heartbeat of dust and reflection. In the end, perhaps what draws us most to this discovery is not its novelty, but its reminder of perspective. For millennia, humanity has gazed upward, tracing stories among the stars, stories of gods, of destinies, of meaning. Yet even now, in an age of algorithms and spacecraft, the cosmos retains its power to surprise us. A faint blur in a single frame can ignite questions about the origins of everything we are. A handmade telescope can alter the course of scientific thought. And one individual, working through the silence of night, can awaken a sense of wonder shared across the world. S2025 V1. Borisov will continue to drift, crossing the inner solar system and fading slowly as it travels outward. By late spring of 2026, it will likely dim